Here we go. Magnetism is the second to last topic of the school year. It's a reasonably simple topic based on the way we're going to do it. So here I have a fun little diagram along with a weirdly tiny definition for magnetism. So it's the physical phenomenon produced by the motion of electric charge, typically electrons, resulting in attractive and repulsive forces between objects. So here we have a list of basic facts about magnetism, most of which you should already know. So for starters, there are two different types of magnets. There's natural magnets, also known as ferromagnets, and then there are electromagnets. Second bullet point says, well, you can magnetize most materials. So you can magnetize basically anything. You can magnetize plastic, you can magnetize paper, you can magnetize any number of things, because it's just a matter of getting the electrons all kind of spinning in the same direction. Problem is, it's very difficult to get electrons in non-metals moving. So, as it says here, metals make much better magnets. The next bullet point. Electromagnets are created by passing electric current through the metal. So basically what happens is when you pass the current through the metal, all the electrons in the current are all going in the same direction, and they in turn get the spin of all the electrons in that metal going in the same direction, which is what creates magnetism. We're going to go into more detail with that as we get into other lectures. Next one says all magnets have two poles, a north and a south. So that's something that we already knew. We're going to actually talk about a fun kind of mind-blowing fact about that later in the lecture in about a slide or two. The next one says you cannot have a monopole. So what does that mean? That means no matter how small you cut a magnet up, it always is going to have a north side and a south side. You take a magnet, you cut it in half, you've created a new north and a new south, but it's always going to have, each chunk is always going to have its north and its south. No matter what, even down to the atomic level, you cut it up, it's going to still have a north pole and a south pole. So it's kind of a fun, interesting thing that is kind of cutting edge physics at this point that they're trying to figure out still. And the last one, which everybody should know, like poles repel and opposite poles attract. Okay, this is going to be kind of the crux of the entire lesson here. We're going to talk about magnetic fields. Magnetic fields, just similar to electric fields, are just a region of influence. So in this particular case, it's a region of influence of a magnetic force on an object. And we'll talk later what specifics have to be true about that object. We're going to talk about that in a subsequent lecture, about the fact that it has to have charge. Oh, that's terrible. And it has to be moving. And there's even a specific way it has to be moving, which makes it a little bit tricky. But that's for another day. Today's an easy lesson. So, what I wanted to point out and really kind of hammer home is that there are major similarities between electric fields and magnetic fields. It's what makes them so kind of easy to discuss after having beat you over the head with electric fields. So the first one says the density of the field lines denotes the strength. So that just means if I have electric field lines that are far apart, or magnetic field lines rather that are far apart, it's not a necessarily strong field. But if I start packing more of them in here, that becomes a much stronger magnetic field just based on how many I have packed in there. The next one, and for a similar reason to why it was with electric fields, the lines can never cross. So with electric fields, it's because they denoted the direction of a force, and you can never be basically accelerating in two different directions at the same time. We'll talk in a couple slides about why it's the case with this. Okay, the next or last bullet point on this page says the lines have a specific direction that they point. So just like with electric fields, they always pointed away from positive particles and towards negative particles. Same thing kind of goes here, only it's a little bit different. So what we're going to talk about is we're going to kind of go take a quick aside here. We're going to talk about compasses. So we've all seen something that looks like this. It's a compass. So a compass is just a device that's comprised of a small, lightweight bar magnet. So that would be this here, where this is the north side of the magnet and this is the south side of the magnet. And it's on a pivot. So it's basically on this thing. We're looking at it from the top. So it's kind of balanced on that thing and it's allowed to spin in either direction. So it can spin pretty freely. There's very low friction in here. And it's set up that way so that it can line up with the magnetic field of the Earth. Now, here's a nice mind-blowing fact. If the North Pole of a magnet is always attracted to South Magnetic Pole, and the North Pole on the compass needle always faces the Earth's geographic North Pole, it's kind of hard to get around realizing the fact that what we call the North Pole is actually a South Magnetic Pole. And if you didn't want to believe me, I assure you I didn't draw this picture myself. This picture is in virtually any textbook you ever look at. So our North Pole, if you look at it here, I'll change the color so you can see it a little bit better. Our North Pole is actually a magnetic South Pole. Mind blown. So, now how does that help us decide the direction of magnetic fields? Well, magnetic fields always point in the direction that a compass would point. So, basically the direction that the North Pole on that little compass, so this guy, would face would be the direction of a magnetic field. So if this were a compass just kind of hanging out on Earth, this would be the direction. Let me make that a little bit. This would be the direction that the magnetic field was at that location on Earth. So, in reality, that just means that if a magnetic field always points the direction of the compass, it always points away from the north, because remember, the north side of the magnet is going to be repelled by the north side of the magnet, but rather the north side of the compass is repelled by the north side of the magnet, and it's attracted by the south side. Now, let's look at this diagram for a second and we'll discuss it. So if I were to place a compass here, the north side of that compass, the north needle, would face away from this north, right? And the south would be attracted to this, so it would point towards it. So we're always going in the direction that the north needle is pointing. So at all points, it would be pointing away from the north and towards the south. So if you want a fun little mnemonic device for this one, well, magnetic field lines are Santa on Christmas. They're always leaving the north and going south. So here are some diagrams, again, looking very similar. Excuse me. Looking very similar to the electric field diagrams we did. Note the same statement we just made. They're always going from the north towards the south. Now, there is no south here, even though technically I know what I said before. It has to be a south. It's just out of the picture. It would be over here. It would be over here. And far enough away to not be really messing with the localized magnetic field here. So, it shows the magnetic field lines leaving here, has that similar feel where they're never kind of going into each other and they're certainly never running into each other. So let's just talk about that for a second. I said before that before this lecture was over, I would explain to you why magnetic field lines can never cross. Well, if I have a compass that happens to be facing this particular direction, that means that my magnetic field line is there. Now, if I had another magnetic field line going this way, that would say that somehow this magnet or this compass would have to be facing both this way and that way at the same time. And that, my friends, cannot happen. So, this was a reasonably quick, simple lecture on magnetic fields and the very basics of magnets. Now, I understand that you had a rough week already because you had that test that was due Tuesday at 11:59, which is in about 3 hours from when I'm recording this. So obviously that had to get done. So the assignment that's associated with this one on Castle Learning is reasonably short and reasonably simple. So that will be the only assignment I'm going to expect you guys to have ready for us to go over on Friday. Only other things I want to remind you of is remember now that those assignments are due before our Zoom classes. Alrighty, so that's that. Short, sweet, to the point, and I will talk to you guys on Friday.